Okay, very good. So, well, thanks everyone first for being here on a Friday afternoon. Afternoon in Europe, maybe it's a morning or late or evening in other parts of the world. And as part of this Virtual Infinity seminar series, I am going to today present basically work that is based on this preprint that is shown at the bottom of the screen, and whose extra material is in the GitHub repository right underneath. And I'm actually very happy to be able to talk about this project I've been working on for a little bit. And it's mostly deals with using conformal counter-Penrose diagrams for the visualization of hyperboloidal slices. And well, let's go straight into it. Again, I suppose that these things will be known by everybody or almost everybody in the audience, but let me just go through the steps just in case there's somebody who's new to any of these topics. So first, one useful way to visualize space-time are conformal counter-Penrose diagrams. An example is shown here on the, you can see my cursor, right?
Yes.
Thanks. So here on the right of the slide, there's an example. This is Minkowski, compactified along the null directions. So the idea about conformal diagrams is that the compactification happens along the null directions, because in that way the causal properties of the space-time remain the same. So the angles remain the same. And here the solid lines are nothing but t equal constant slices, so level sets of the usual time coordinate that we use in Minkowski. And as we can all see, all of these extend from the origin, which is at the vertical line on the left of the diagram, and they all extend to space like infinity, I0 on the right. But now we're going to focus, as this is on a series on hyperboloidal topics, we're going to focus on hyperboloidal slices. And one conceptually simple way to obtain hyperboloidal slices from the usual Cauchy slices, which were shown before, are using this height function approach that I will also talk about later on in order to construct these slices. And just let me, as you may have already heard, but let me state it once more, that hyperboloidal slices are space-like and smooth, as we can see for this example in Minkowski, but the main interest we have in them is that they reach fictional infinity. Well, technically also partial infinity, depending on how you choose your height function. But we're interested in the fictional infinity. And here the green lines in this Penrose diagram of Minkowski depict level sets of the new t without tilde, which corresponds, I'm going to be calling the hyperboloidal time, which gives the slices which all reach fictional infinity here. And as one first example before going out, well, okay, let me just give you a bit of the infrastructure so I can then talk about more details in later on in the talk. So I'm going to restrict to spherical symmetry. That is what's usually done in most Penrose diagrams. There's things one can do if in axis symmetry, more general scenarios, but there's limitations due to what you can depict, let's say on a piece of paper. So spherical symmetry, the line element I'm going to consider has either the form on top, which with usually GTT, GRR, G, theta, theta, in the way I'm writing them here. And the second line uses them in the way that is actually evolved in the numerical simulations that at some point I will talk about later when we talk about the dynamical spacetimes. Just the components. And one way of actually finding this height function is that changing the time coordinate in the line element allows us to relate the metric components to the derivative of the height function. So if we choose the first choice, it would have just GTR over GTT, and the other one is going to be a bit more complicated expression, but this is exactly equivalent. And so this can be used for all the spherically symmetric metrics that I will consider. And I'm also going to focus when in most of the explanations, the example we use CMC slices. CMC stands for constant mean curvature. That means the trace of the vesicle extrinsic curvature is constant on the whole slice. But as we'll see later on towards the end of the talk, for numerical data, that will no longer be the case. But this expression should still be generic for that. Yeah, so this is the basic concept. So we're going to deal with the metric on the one hand, and from that, we were going to get the information we need to construct the height function that using this will allow us to just plot the diagrams and look at them. Right, and as I was mentioning, one example here is to consider Minkowski, as we saw it before. That should correspond exactly to the purple lines on the diagram on the right here. So Minkowski just completely empty space-time. Okay, a hyperboloidal slice of Minkowski. If you see the purple slices, they reach future null infinity. And within this way of setting the metric, this quantity chi that we saw right here, this is the spatial conformal factor, is exactly 1 because the space-time is empty. If you were to perturb that space-time, we'd say with a scalar field, for instance, you can see the example of this scalar field perturbing Minkowski, which is obviously no longer Minkowski because there's some energy in it. Then if you solve your Hamiltonian constraint, one way you can reflect the presence of this of the scalar field is because now chi spatial conformal factor has a non-trivial one. Okay, it's 1, so it's going to be something which differs from 1 due to the presence of the scalar field. And if you now use this expression to read off from your metric what your components are and construct your height function and then create the Penrose diagram, then and you use that using the okay, all the details are in the paper, but basically you would just follow the usual procedure to construct your Penrose diagram. And then you will see that instead of the purple lines, you're going to see the black lines, which are chosen so that the purple and black lines will coincide at future null infinity. But in the interior of the domain, the black lines look different because there's the presence of the scalar field. Okay, but now, as you remember in the title, I'm talking about strong field hyperboloidal slices, so we're going to look into that. But right before that, as last bit of the introduction, to provide all the necessary materials to follow the talk, let's talk a bit about the trumpet geometry. I'm especially interested in evolving with punctures, that is slices that enter the horizon of the black hole. And that's also because they allow to be able to make all these nice diagrams and pictures. But what happens if you want to use the puncture evolution, that means that you're going to use a slice and not cut it right inside of the black hole as you would do with excision. So here on the left of the slide, we have 2 diagrams of the Schwarzschild spacetime. On the top one, we're seeing a wormhole slice that extends from space like infinity all the way into the black hole and out the other asymptotically flat end. And this is the initial data would normally be used to start with as initial data. But if you take that and evolve it with the moving puncture gauge conditions, what is shown on the right is going to happen. So you start with this slice, t equals 0, and you evolve in time, and due to the effect of your gauge conditions, more specifically the shift, which is the beta, your grid points are going to be pulled out of the asymptotically spacetime as you out of the asymptotically flat spacetime outside of the black hole as you move forwards in time, and then at some point you're going to be numerically disconnected from the original end of the slide, and you're going to get one of these lines on top here of the diagram, which look very similar to a trumpet slice, which is the trumpet slice shown on the left down, which extends all the way into the black hole, but it does not reach the area inside of the horizon. But what happens is that as it gets close to the singularity, at a finite value of the Schwarzschild radial coordinate, the proper distance becomes infinite, so that it never actually reaches a singularity. And we can see that in the embedding diagram, which is here, the part which looks like a trumpet. That's why this is called a trumpet. And the nice thing about this type of slices is that they allow to give to provide data for all of the quantities which are evolved numerically, and finite everywhere, and not and avoiding the singularity. So I'm going to focus on these type of slices now when constructing the diagrams. If there's any questions so far, feel free to ask, or at any point during the talk.
So maybe can you repeat the advantage of the trumpet over the wormhole? Because at the end, it looks like they're both doing similar things.
That's a very good point, yes. So, I mean, as far as I know, and if somebody knows better, please comment on this. I am not aware of any way of evolving numerically where you have the wormhole as a stationary solution, or the solution that your data become like tends to. With the type of gauge conditions normally used with this type of simulations, what starts as a wormhole becomes a trumpet at the numerical level. I cannot think right now of any advantages that the wormhole data, so the top, would have over the bottom one. But in both cases, that is true. You would be getting data which are finite on your domain, except for the actual point at the very end, which is, yeah. Does that make sense?
Yes, thanks.
Thank you. Okay, so then let's jump into the thing, and this is actually what the one of the parts of the paper aimed to achieve. This is as compared to this. These are hyperboloidal trumpet slices. So instead of reaching space like infinity on the right, they reach frictional infinity. But now let's look into how to construct this and what and how some of the details that help when making this type of diagrams. So there's first thing to notice here that I'm calling something R tilde trum. This is for the innermost Schwarzschild radial coordinate that is reached with the hyperboloidal trumpet slices. So no slices will get closer in terms of the Schwarzschild radial coordinate than 1.91 to the singularity, because the singularity is avoided. That's what I mentioned before. And depending on the slices you choose, that changes depending on yeah. And these again are constant mean curvature slices. Now, if you notice, there's slices here in black, and there's other ones in orange. And if you look at the ones in orange around this area, around the horizon, close to the bifurcation point, they don't look very nicely because they sort of seem to go up and down. And that is an effect purely numerical from the integration, from the way that the height function was integrated from the metric data. And let me now show you the way that the height function looks in order to understand where this comes from. So if you use like just your usual Schwarzschild coordinates and you integrate your height function, it's going to look exactly like this orange curve here. So let's remember, this is the uncompactified Schwarzschild coordinate. The horizon is located at r equals 2, because I'm choosing m equals 1 for the black hole's mass. So here we have a divergence in the height function. If you go closer, so remember that at 1.91, we have the location of the trumpet. Now the height function becomes diverges there, also becomes like minus infinity. That's the way that we are avoiding the singularity. And if you look to the other side, okay, if you were to just keep going for larger values of the radial coordinate, the height function would basically grow, because that's the effect. The effect of the height function is to raise your slices so that they will reach frictional infinity instead of space like infinity. And indeed, however, as you can guess, if we're trying to integrate a function that diverges like this at a point, things may not be, it's tricky at the numerical level. So that one way of actually dealing with this is to separate the height function into a part, delta h, I'm calling it like that, which is finite around the horizon, and this f function, which takes into account this divergence, which actually for Schwarzschild can be taken to have exactly this form, minus 2m logarithm of r over 2m minus 1. And so, for instance, if you have your closed form expression and you take away this f part, then you can integrate for delta h, and that is going to be something perfectly smooth around the horizon. And indeed, then you can just plot, and all these slices look perfect here for the way I have chosen to create diagram. So that, again, it's a little detail, but it makes quite a bit of a visual impact if you're trying to make nice plots from your data. And also imagine that when you don't have a closed form expression, but you actually just have some numerical metric you're trying to plot. Right, next is that, so we've been talking about how to calculate things in terms of our uncompactified radial coordinate, which is, let's say, the usual Schwarzschild coordinate here. Now, in the hyperboloidal evolutions we aim to, well, we're working on, in order to reach fictional infinity, we need to make a compactification of our radial coordinates. So we don't work with r tilde, which extends all the way to infinity, but with r, and r is chosen with this compactification factor omega bar that goes to 0 at scri, so that for a specific value of r, which this r scri it just be 1, so that infinity is mapped to r equals 1. That's what I'm trying to say. So now infinity corresponds to r equals 1, and that's the location of scri plus on our domain. And not only that, but if we are dealing with the metric components are going to diverge, and after this compactification of the radial coordinate. So for that, we're going to work with this conformally rescaled metric G, which is finite everywhere, including fictional infinity, because it is the product of multiplying the omega squared factor, where omega is the conformal factor that goes to fictional infinity to 0 at the appropriate rate, times the actual physical method that diverges. So one thing balances the other, and we have something which is finite. And the point of conformal compactification is that this omega bar and this omega actually behave similarly near scri. That's why the effect of one cancels the other. That's the basics of the construction. I'm not going to go into more details of this because it's especially relevant for the evolutions I'm not going to be talking about today, but that's at the back of all of this work, because basically I worked into all of this to be able to understand the simulations I was seeing. And now, just to show you that the most complicated expression I'm going to show today, there's more equations in the paper. This will tell us how to integrate the part of the height function which is non-divergent at the horizon, so the delta H, from taking our metric components, which may just be numerical data from the simulation. And I'm including here this C factor, apart from all of the metric components I showed before, which does not correspond to light speed. It's just a factor that, in my experience so far with the gauge conditions I've considered for hyperboloidal evolutions, especially with trumpet initial data, at some point, the time would get rescaled, and this C accounts for the rescaling in time. So in order to create the plots properly, this C factor has to take into account. The takeaway message from this expression is that you can take your metric and calculate the height function from this data. And and if you do that on the compactified domain, we can see how this looks as compared to the previous plot I showed, this plot I showed here. So now if we deal with everything on the compactified domain, here I am showing the blue corresponds to what we had before in orange, only that here, if you notice the range of the radial coordinate, it extends from r equals 0, that corresponds to the location of the trumpet, all the way to r equals 1, which corresponds to the location of scri. The height function, as we can see on the left, diverges at the trumpet, as I mentioned before, and it also diverges at r equals 1. That's why instead of plotting the raw field h, the raw quantity h, I'm multiplying it by the conformal factor that goes to 0. And we can see that omega h actually is finite at fictional infinity. And indeed, the way this was constructed, I actually just integrated for delta H, which is shown in black, same as before, and then add to it the F quantity, which again, you can calculate here from geometric components, or you can use the expression for Schwarzschild if you're dealing with Schwarzschild. And all of this is being compared here with the Minkowski height function all of these are constant mean curvature slices, and they all behave the same at functional infinity. So, and I am now doing this detour to explain how this can be done in the compactified radial coordinate, because everything is much more straightforward within the same picture of having the code that evolves on a compactified radial coordinate, and also making these plots, the conformal Penrose diagrams, also using the same radial coordinate, because actually the diagram doesn't really care what radial coordinate you use. And that is so far as the first part that deals with this, how to integrate this height function for static structured data. Now, we may start with such a slice, like this, and then we're gonna, okay, now we're gonna use this initial data, maybe some small perturbation, and just let it run within our hyperboloidal code. And if you want to see how those slices behave as the evolution moves forward, one way you can use is to take advantage of the Connell equations, which are here. They basically state that null coordinates remain null. And these actually split into advection type equations. So one for the retarded time u tilde, so partial, so this is all right. The first line here is in terms of all of the uncompactified, unhyperboloidal anything. So this is just your retarded time and your forward time. And here these C plus minus are the physical propagation speeds. If you make all of the transformations that you would perform on your coordinates in order to create a Penrose diagram, you will end up using this capital R and capital T, that's the way I call them in the paper. And these are actually nothing but what you plot on the diagram. So T is what you plot on the y-axis, and R is what you plot on the x-axis. And if you plot one against the other, you get exactly the Penrose diagram. And it turns out you can, for those data, you can just evolve these quantities R and T. You find the equations here at the bottom from the ones at the top. You can actually just, it's straightforward to see step by step. And where here, these beta, alpha, chi, and gamma are metric components. These can be evolved. This will evolve indeed with the space-time if some dynamics is happening, be it just gauge dynamics or actual physical dynamics. We're going to see an example of each of them in a minute. And this allows you to take your initial data for the Penrose diagram and evolve it together with your simulation. And I thought that was quite a cool thing to do, to be honest. And let's see the first example. So this starts with these slices here. These are constant mean curvature slices of Minkowski, like the ones we saw before. And now I give this initial data for T and R and evolving time together with the Einstein equation. And this is what happens. It was a bit fast, so I'm going to run it again. What happens is that you will see how the slices move up. That's because time is passing. And now you see how all of the points basically are moved towards the top right of the diagram, like this. This is the effect of the gauge condition, more specifically the shift condition. And this is exactly, let me go back for a moment, the same effect that we are seeing, that we saw before in this diagram from this paper by Baumgarten. So the dots have actually been moved out of the domain, and this is the same thing we're seeing right here. And for me, the relevant thing about this diagram was not only to be able to see how they just evolved in time, to be able to see the fact that the initial constant mean curvature slices, which are depicted in blue here, after some point, due to the choice of gauge conditions, are no longer constant mean curvature. So the trace of the extrinsic curvature is no longer constant. And that corresponds to the black lines. Here, the way I created this diagram is to evolve for some given time and then just make the times coincide at functional infinity, so that we can see the initial slice in blue and then the final ones where the stationarity has been reached for the metric components in black. And we can see how the black lines actually, in terms of the Schwarzschild radial coordinate, get a bit closer to the singularity than the initial blue lines. This is also depicted here in the dashed lines are the innermost values of the Schwarzschild coordinate that can be reached by the slices. Here, this effect is just a gauge effect. There's no actual physics going on. This is always Schwarzschild. It is a static solution, but we're having some trumpet relaxation because the initial trumpet changes a little bit due to the choice of gauge conditions. Any questions so far?
I'm curious to know how sensitive is this, like, in terms of making decent data for the T and the R that you're evolving? How sensitive is that against the shift condition that you use?
So something I did notice is that when creating the data, it is not seen here, but if you get like very low, like this blue line, which is at the bottom, like the last line here, the blue one, part of the slice actually quite steep around the horizon, even if it doesn't look steep here, but it looks steep on the actual, if you just plot UR and UT against the compactified radial coordinate. So that cannot deal not well numerically, but that is unrelated to the shift. With respect to the shift, I think I would have to say this a bit more because so in which way would you expect the shift to be the problem?
So in the past, when I was in Jena, we did evolutions like the thing that you're doing, but just without any of the compactification. So it was way simpler than what you're doing. And there, what I saw, I mean, without saying any details, right there, what I saw was that as soon as I turned on the gamma driver shift, constructing the space-time diagrams was a complete mess. Really failed.
Okay, you mean to the sense
I mean, maybe
that
it was just that I was doing something stupid, right? But I'm just curious to know how you, like, if you struggled with that, or if it just kind of worked out of the box for you.
These are such worked out of the box. I'm aware how many points are being lost in a way. So what I would like to understand is any ways of actually improving this, which I suppose that relates to what you're saying. But I have not really done any further research on this aspect. Sorry.
No need to apologize. Thank you.
I'm not sure I understand this phrase that where you lose the points. So in the evolution, it looks like the slices are mostly being shifted along the flow of the time, like killing field, if there were a time. I mean, right? So you're just shifting them towards the future. So anything you do in the Penrose diagram will look like this, right? Because the flow is always towards I plus, and from inside it's going also to the right. So are you really losing something, or is it just like if you shifted them back so that they have always aligned along the future null infinity?
Yeah, no, you're right. I mean, I was being a bit sloppy with the wording. No points are lost. Basically, they are all are moved towards future null infinity, as you say. But of course, for the purpose of being able to visualize what is happening, that is an undesired effect. So what we would like to do, at least for the part of the data for the conformal diagrams, is to be able to keep them within the domain so that we are still able to see better. I mean, this example is not very relevant because in the end, there's no actual physical dynamics, but as we'll see next, in the case of the collapse, you may be interested to actually keep the points like inside of the horizon for longer. But yeah, no, I guess it's just a way of finding a way to better deal with this at the numerical level, I guess. Yes. Okay, so then let's move on to the next. Oh, actually, no, before that, there's an example. I just put this plot. There was actually a check mostly for myself that I included in the paper. This shows so let's focus on the red and the orange lines. These are the values of the big R. So this is actually what you plot on the x-axis when you make the conformal diagram. And they correspond to two different. So they are okay. There's this the two. So you can see actually two orange lines and two red lines. They are meant to lie on top of each other. each of them like separate because they correspond to different times, but they correspond to the same slice. Because you can start if you start your simulation at an earlier time, then just basically your slices will have to move a bit later to be able to reach the same one if you started later. So those okay, maybe I'm not making much sense, but the idea is that the dashed dot line and solid lines, the red ones coincide and the orange ones coincide. And then on top of that, you can see like these thicker dashed lines, the black one on the red and the gray one on the orange. These ones have been constructed using the height function I was talking about before. So using exactly, this expression here, pretty much. And this also counts in the plot I'm showing the effect where on the main graph, I'm taking into account this value of C, this factor I was mentioning that by which the time gets stretched in the trumpet evolutions, and we can see that up to some extent when on this around r equals 0.95 here, the lines go bad. That's because of scry and things diverging. But I mean, I'm not really worried about that. Other than that, the coincidence between the curves is quite good. What if you don't take into account that value of C, which is the inset on the right, then you can see how the lines clearly do not line up each other. That was a check for myself to actually check that the way I was calculating the height function was correct, and that coincided with numerically evolving the slices using the iconal approach. Yeah, I can go into more detail later if you would like, but this was mainly meant as a check. But now let's go into what's more interesting, which is the actual physical process going on, which is a collapse scenario. This is an example of the pendulum that we're going to see. I've shown this before. Sorry if you have already seen it, but let me just show it again to understand what's going on. Here we are seeing again Minkowski, so a regular spacetime perturbed by a scalar field. The scalar field is depicted in purple. This is the signal here in the middle, and we are also seeing other metric quantities and the trace of the extrinsic curvature shown here as well, and we're seeing again between r equals 0, which is the origin at the regular spacetime, and r equals 1, which corresponds to the location of functional infinity. Now, I'm now starting the movie. Hopefully you can see this well enough. Part of the initial signal has left through scry. The other one is moving towards the origin, and it's going to now collapse to a black hole due to the energy concentrated there. The vertical line here corresponds to the apparent horizon of the black hole that has formed. And now r equals 0 corresponds to the location of the trumpet of the black hole spacetime that we have now, whereas r equals 1 corresponds to scry. And so evolving the initial data in R and T for an equivalent collapsing scenario on hyperboloidal slices gave the following data, basically. So this is still collapsing, and here that's where collapse happens. And now the effect of the shift, as we were talking about before, basically pulls out the points towards functional infinity. Let me just run it again, but this is what is happening. So at some point, just formative time, and then collapse happens, and the slices get moved. And now we can see this. Just all of these slices on the same plot, because basically here time is just moving up, and we can see the slices. And the difference between the plot on the left and the plot on the right is that the initial slice chosen for the simulation was a different one. Basically, what is constant is the time between the slice reach and the moment where the collapse happens. But actually, they're just equivalent. And so that is the content that I wanted to talk about from the paper. And to finalize, it would make sense to...
Alex, sorry, could I ask one more question?
Of course, yeah.
What is the black line there? Is that actually like an approximation of the event horizon, or is it just a nice line at 45 degrees that you liked?
It's more the latter. That this line here does not correspond to actual data. it was just so indeed 45 degrees, and it was chosen so that the lines, so the hyperboloidal slices would basically accumulate as because so in Appendos, even if in the simulations time is not compactified, you can evolve forever. I mean, you'll have numerical trouble, but you could in principle evolve forever. In Appendos diagram, time is compactified. So as you move forward in time, all of your slices are going to accumulate near time like infinity. So basically, after some time, you could see how all the slices were accumulating here, and I chose that as the vertex from which to actually create the 45-degree line. Yeah, thanks for the question.
Can I continue on this question, perhaps?
Sure.
Because it was also, I think, so not only the horizon black line, I suspect that the all black lines are things that doesn't come from the simulation. Am I correct? I mean, because in principle, in principle, we have the data on the first blue line. So everything that's below this, I mean, is not information there, right? And then you are kind of constructing as you move up. So, okay, so this makes sense, right? I mean, all these black lines are things that you draw afterwards based on some quantities that you had already. Okay.
Yeah. So I actually have you can see what I'm showing here. Obviously not the letters, but okay, yeah. So, but what you see in color here, that is the actual numerical data, and we can see as it moves in time. This is what I get from the code, and then I am plotting it, and then I'm putting those lines that I was showing before. But this is the what is moving here is what I get from the code.
Well, even this, sorry to interrupt, even this, you have this freedom of shifting along the time-like killing field of the reference metric of the background that you're using to map it to, right? You're mapping this dynamical evolution to a reference background, which has a time-like killing field. So you can actually, while it's evolving towards the future, you can still pull it back after the horizon has formed.
When you mentioned the background, okay, maybe I'm not understanding your question properly, because I mean the simulation itself has no background. This one,
not the simulation, but the mapping to the Penrose diagram, I think happens. So let's say previously you were showing slices on a Schwarzschild Penrose diagram, right?
Yeah.
And similarly here, well, this is a collapse scenario. Obviously, this is a dynamical scenario, but eventually you form a horizon, and there you have the freedom. Let's say you evolve towards infinity in time.
Yeah.
The way you map it to the Penrose diagram, you have a freedom where time starts and how much. And then so you can pull it back along the time-like direction. So it will look different on the diagram. I think that's part of the confusion that I have when I see an evolution on the Penrose diagram, because Penrose diagram is inherently very misleading about distances, in particular distances in time. So when you go forward in time, everything will be near the time-like, future time-like infinity. But you can still pull them back. And I think maybe that's related to what Rodrigo was asking. Like there is this freedom how you represent that slice.
Yeah, I guess that's those. I mean, all of this is valid once you have reached stationarity. Before you reach stationarity, I mean, that's when you're like changing, and then I guess that one has to be far more careful in that moment. But once, I mean, definitely by the time I'm showing now, definitely stationary has been reached. That this is just moving forward in time. So in that case, yes, you can read it to the background, and yes, you should be able to move it up and down. Yeah. Indeed, for instance, if I to go back here to the plot. Here in this plot, that is exactly what I was using. So in order to compare the dashed thick lines to the other ones, I was indeed moving moving up and down in time to be able to actually get them to coincide exactly with the comparison. So yes. But yeah, so I suspect that I have not answered all of the questions properly. So if you could remind me of what is missing, I'll be very grateful. No? Okay, well, if there's anything left, we can finish the discussion after the talk. I would just like to again mention some of the things that related to this, I think would be really useful to continue like on the hyperboloidal quest that we are all pushing forwards in different from different directions. And more specifically, so as I mentioned, I like the puncture approach because it allows to go more inside of the horizon. And even if, as we can see by default, the gauge conditions do pull the grid points out of the horizon, it's still possible to gain some insight of how the slices look inside. And so I'm trying to understand how to go beyond the spherically symmetric examples that I have shown. I need to indeed mention that from the apprentice of 2008, the work by Bochman, Pfaff, and Badin on binary initial data and hyperboloidal slices, where they adapted the Bone-York approach to describe boosted and spinning binaries. And indeed that goes forward with some work also by David Schinkel and Rodrigo Panoso Macedo. And so this work here was basically used with excitation in the sense that the horizon penetrating coordinates were basically cut once you were inside of the horizon. I would like to go beyond that and understand how to set up things so that we can, in the future, use a puncture approach that works on hyperboloidal slices. And for this, one of the things I think is quite relevant is to be able to, same as I was talking so much about Schwarzschild trumpet slices, I would like to see, is it possible to obtain Kerr trumpet slices, even if, as done in this work here, slices which are asymptotically constant mean curvature, because maybe it's not possible to have a fully constant mean curvature Kerr slice, same as Kerr is not conformally flat, maybe this type of limitation. I would like to understand this better, so I think it'll be a nice something to think about. Then something I've been lately thinking about is to be able to take a Schwarzschild trumpet, as the ones I was showing, and just off-center it, like make it be located at the location which is not just the center of the coordinate system. It's just a coordinate transformation, but it's not clear to me how to do that. I don't think it's completely trivial. And also, as I'm writing here, like going beyond spherical symmetry, because this will be going beyond spherical symmetry. It's just the same concept, but you'll be moving it around, and at the description level, things become more complicated. So the trumpet is no longer at r equals 0. It's going to be somewhere off-centered. But still, this ellipse I'm showing here is just meant to be the end of the height function, and that should correspond to functional infinity. So we'll be seeing the complete, this embedding diagram would include all the way up to infinity. And this is basically, down here is the trumpet, of course, as we said before. So that's something I would like to understand things better. It doesn't seem to be, it's conceptually simple, but at the technical level, it may not be as much. Then also like consider, okay, I wrote also here Schwarzschild because that's the simplest, but of course, if the Kerr slice is available, that would be even more interesting. And then to consider a trumpet, which is boosted, like something we could use later on, okay, because the next one is going to be, okay, let's have two trumpets and let's boost them to have a binary, or just start with two off-centered ones and see how the head-on collision happens. And again, I'm putting the emphasis on the word trumpet because I would like to see how this works for punctures. Yeah, so this is what this work, like how I would continue different ways from here. And all of this is done indeed because we want to be able to have initial data that's going to be suitable for numerical simulations, evolutions that we do on hyperboloidal slices. And this is just some work in progress on that. I'm just showing some quantity which is evolving on a hyperboloidal slice from the Einstein equations. And that is all I wanted to say. Hope it was more or less understandable. I'll be more than happy to answer questions that you may have.
Thank you, Alex.